So what we were discussing about is, can you write this? Why we were doing it, this method at the first instance, right? Why we suddenly wrote B0, B1 out of the blue, and then we started doing some calculations. Then I started saying to you about finite difference, first finite difference, second finite difference, third finite difference, and it got a bit complicated also. Then I told you to write the system of linear equation for this. Now, what system? Can you tell me? Who can tell me this? What is the benefit of this? What is the benefit? This is a system of linear equation. Now, how good it is from this system of linear equation? Anyone? Here it is a proper matrix V. Okay, but the matrix which you will get after writing it is something like this. Can you tell me one? Then all are zeros. Yes, then x1 minus x0. Others are 0. Then so on. You continue the matrix so on. Then what the last entry? Then multiplied by xn minus x1. So on till the last element will be the product of xn minus xj. And yes, you have j equals to 0 to some n minus 1. You have this matrix. Okay. And then on the right, what you have? B0, B1 till. These are the unknowns you want to find. What is on the right? Yn. Can you see that this is a low triangular matrix? Inverting a low triangular matrix is easier than that of the Vandermonde matrix. Okay. So purposefully, you can think that this method is even more efficient than that of the previous method I told you, using the Vandermonde matrix. But this is just the interpretation I want to show, but we won't compute the inverse of this. Okay. There is an easier method even than that. So can you tell me now, what was our expression? Y equals to B0 plus B1 into x1 minus x0 plus B2 into, tell me. In your notes have written it. Totally wrong. Yes, it is a polynomial, right? So how can it be a constant? X minus x0, then B2. Yes, like that you continue. Okay. Now we found what is B0, right? Y0, good. Y0 or Y8 x0, right? Y0 or Y8 x0 plus B1 is can you tell me in terms of the notation? Y of this x1 x0, is it? Into this x minus x0 is still there, right? Plus what is B2? Yes. Is it correct? Multiplied by? Fine. Then so on. You can carry on. Now you can see that you have an explicit expression to compute this polynomial, to compute this Newton's interpolating polynomial. Can you see? You already can compute this guy. You already know this. You can compute this one. And you already know these points. And this is the x, which is giving you the polynomial. Okay. So this will be a function, y will be a function of x. This we will see in action right now. I will show you what does this guys mean actually. This is very unintuitive to you, but remember that I told you that these represent some kind of slope. Okay, we'll exactly use that. Okay. Fine. Let us see. We will use something known as a zigzag rule. It is known as a zigzag rule. You will see why it is known as a zigzag rule. Okay. So I'll give you three. We'll start with a very low amount of data. Then you can scale your whatever you like. But you should understand the method for a small number of points first. Okay. Suppose I will tell you that you have xi. What does interpolation mean? You will have a set of data points. You will have a set of data points given to you, right? And your job is to find a interpolating polynomial, isn't it? So I will write the set of points to you, xi and ya. Let xi, ya I have here is for x equal to 0, you have ya to be 1. For x equals to 1, you have ya to be 3. For x to be 3, you have ya to be 55. Now I want to, you have these 3 data points. How many data points are there? How many of you are saying 2? How many of you are saying 3? Yes. So there are 3 data points. Good. So you can see that there are 3 data points. Good. So now, how can we construct a Newton interpolating polynomial based on these 3 points? So you have x0, x1, x2. Let's start doing the interpolating polynomial construct. Okay, I'll tell you the method first, and I will give you, I will do this example. I will give you another example. You will do it here. Okay, fine. So, what is our next step? What we should compute? What we should compute? Hmm? Anyone? What we should compute? Let me know what you should compute. It's like a good song. Yeah. So what we should compute? You should compute the finite differences. You should compute these guys, isn't it? You should compute these guys. And you should need only these 3 terms, I believe, right? What do you think? Only these 3 terms or something more? You don't have x3, I think. x0, x1, and x2. So you will stop here, I think. Only these 3 expressions, isn't it? So you have to find y of x1, x0. First finite difference you have to find. This is the first finite difference, right? And this is the second finite difference. So you have to compute these finite differences. How you can compute it? What is y x1 minus x0? Y of x1 minus y of x0 divided by x1 minus x0. Now, can you think that you can write this guy here? You can write that finite difference here. And just do this. See, this is y0, this is y1, this is y2, x0, x1, x2. This guy, you do 3 minus 1 divided by 1 minus 0. This is the first finite difference, isn't it? Agreed? First finite difference. So, can you tell me what it should be? What I should write here? What I should write here? 3 minus 1 divided by 1 minus 0. Yes. Agreed or no? Let me make it more easier, maybe. Just to make it simpler. This is y1 minus y0 divided by x1 minus x0. This is the first finite difference. So this is, can you tell me what should I write? 3 minus 1 divided by? Okay. Now this is another finite difference which we might need, which you will need, of course. I will tell you why. y2 minus y1. This is another difference. y2 minus y1 divided by x2 minus x1. Isn't it? What is this? 55 minus 3 divided by? Okay. This is the first finite difference. Isn't it? Okay with you? After that, what you compute? So you know this guy now. Do you know this guy? Do you know y of x1 minus x0 now? Y of x1 minus x0, do you know? You know. Then what you want to compute next? Yes, exactly. You need now next is y of x2, x1, x0. That is the second finite difference. What is the second finite difference formula? This formula was y of x2, x1. Then y of x1 x0. Yes. Okay. So can you see that we have, so what is this guy here? This was y of x1 x0, isn't it? What is this guy here? Below I have written y of x2 x1, isn't it? Yes. Now there will be another guy here, which is this minus this divided by x2 minus x0. Can you see how it is flowing through? Can you see how it is flowing through? We are actually approaching this way. It is getting short. It is getting converging to one quantity. Okay. So what is this quantity? Can you tell me? This is the second finite difference. What is this? 3, this is 2, this is 26, is it? So second finite difference should be 26 minus 2, because this is y of x2 x1, this is y x1 x0, and you have exactly these quantities on the numerator. So this is 26 minus 2 divided by x2 minus x0, that is 3 minus 0. 3 minus 0. So 3 minus 0. So it is 8. Now can you tell me what should be the polynomial then? What should be the polynomial? So you found the finite differences, right? You found the first order finite difference. Can you tell me what is y? What is y? What is y at x0? 1 plus y of x1 x0, that is 2, right? 2 times multiplied by what is x0? 0. Plus what is y of x2 x1 x0, that is the second finite difference? 8 times x minus 0 into x1 is 1. Can you see that? So can you solve for this? What is this? Y1 plus 2x plus 8 into x minus 1. Yes, yes, but this is the polynomial we got. Fine. This is the Newton's interpolating polynomial. Newton's interpolating polynomial. Yes. Okay. Now why we need to find this? For any x. Yes. For any x. Yes. For any x inside this 0 to 3. Okay. You cannot compute any x outside of this range. It will give error. It will give error. You have to be within 0 and 3, because that's where you're interpolating things. Okay, you can't go outside of, you cannot compute x equal to 5, not defined. So can you tell me what is the value at y equal to 2? Y at x equals to 2, what is the value? What you do, you just substitute y, this is y of x. So you substitute y x equals to 2 here. So that should be 1 plus 2 into 2, 8 into 2 into 1. What do you get? 1 plus 4 plus 16, 21. So this gives you an understanding. Do you believe this result? Why you believe this result? Any intuition? This is a common sense aptitude question. Why you think this result makes sense? Y of 2 equals to 21. Yes, exactly. Exactly. Y of 1 is 3, then it should ring a bell that when x equal to 3, y suddenly jump to 55. Okay. So then if you are considering a number in between, that is a 2, in between 1 and 3, then that value should have lined in between 3 and 55, and it cannot be a lower digit also. It should be a double digit, because suddenly from a single digit 3, it is rising to something double digit of 55. So it gave you 21, which is acceptable a bit, almost half of 55. Yes. So from that, intuitively, you can think that you did correct. Now suppose you got y of 2 equals to 2. Do you think it is acceptable? Might not be. So this will ring a bell. It can be possible, but it should ring a bell that no, like my function is next value is 55. So it cannot be suddenly decreasing. It is following an increasing trend, right? Everyone got this common sense technique idea? So this is a way you can debug if you are doing mistakes in your interpolation computation or calculation. This I found out myself during my masters. This no one told me. Okay, so I thought like I did lot of mistakes in interpolation when I was doing my master. I did a lot of mistakes in interpolation. Then I thought like all my energies are going in waste and I'm not getting correct results. What should I do? Then I thought how to know whether my results I am getting make sense. So this is how you can make sense. Okay, this is totally based on observations of numbers you are getting. Got it? Shall I give you a problem and you want to try? Now I will give you. I will give you even more set of data points. Okay. Coming to know this method. Okay. I will write this question, and these questions you can consider are important as well. Okay. So what I am asking you to do is, given these data points, how many data points? 6 data points. I want to find the value of y at x equals to 3, which you don't know, but this lies in between 2 and 4. Okay. And you can see these data points, are they equally spaced? How many of you say that they are equally spaced? Equally spaced means the x points are equidistant to each other. Where it fails? Yes, at x equal to 2 and 4. Otherwise, the difference is 1. Yes. So these are non-uniformly spaced points. Non-uniformly spaced points. Okay. And we are trying to do the interpolation. Can you try to find the interpolating polynomial? Observe that I gave you a very long formula, but we are actually visualizing that formula using the zigzag notation. Okay, that is using a graphical notation, writing numbers and computing based on numbers. So what you should do first, you should write them as columns. This is x, this is xi, this is xi, you should write, this is yi, you should write. What you should write? 0 for 1. Then you write, give them a space. You see how I am writing. Give them space. Don't write it in a way like congested to each other. Give them space. For 1, you have 14. For 2, you have 15. Then 4, you have 5. For 5, you have 6. For 6, you have 19. Okay. What is your first idea? You should consider the first finite difference. This is the first finite difference. First finite difference. Then consider the second finite difference. Then consider the third finite difference. Because you have lot of points, technically you should go till you have a single point at the end. Observe that in this formula, how we went and got a single point at the end, isn't it? We got only one point at the end. It converged to that point, right? Do this till you converge to a single point. So you have to consider the fourth finite difference. Fifth finite difference, what you get. And this is quite easy than you think. This is quite easy than you think. If you consider this way, what is the first finite difference? How you do it? See this carefully. I will explain it once. Okay, see this. Everyone carefully see this. Okay, but for the first finite, so everywhere you will have this box. In between these two numbers, you will have a finite difference. In between these two numbers, you will have a finite difference. First order. Okay. Then in between these two boxes, you will have the second finite difference. In between these two boxes, another. Yes. Can you see what is happening? The number of boxes are decreasing. Here 3, 4, 5. Here 3, 4. Okay. Now here there should be 3 boxes. In between these two, for the third finite difference, consider one box. In between these two, another. Now it becomes 3 boxes. For considering the fourth, in between these two, consider one box. In between these two, consider one box. For the fifth, you can see now it is converging to one box. Here you stop because you get only one box at the end. Okay, and you can see how this method is following this trend, which is the same trend, which is exactly the same trend as before. Here, like you can see, it is going like this and going like this. You have to tell me these box numbers. That's it. Okay. I will tell you one. I will tell you one. Then you have to carry out next. What should be the first finite difference? How you do it? 14 minus 1 by 1 minus 0. Similarly, what should be this guy? 15 minus 14 by 2 minus 1. Similarly, tell me the others. So I hope you got the idea. What we are doing here. By doing this, we are calculating all the finite differences. Completed. So, okay. So let us please start telling me the values. Start telling me the values. This is 13, 1, minus 5, 1, 13. Second, minus 6, minus 2, 2, 6. Okay, this one. Okay. Now I'm asking you what should be the Newton's formula, like how the polynomial will look like. This will have a lot of expressions actually, because you are considering fifth finite difference. Okay, ready? Shall we begin? Shall we begin? Shall we begin? Yes. So what should it be? Anyone? Y of x equals to y at x naught plus y of the first finite difference, right? X1 minus x naught. Sorry, x minus x naught plus x minus plus is this correct? Then x minus plus this is the first finite difference. This is the second finite difference. This is the third. Fourth. plus this is the second, this is the third, this is the fourth. Then we have the fifth, the last. Y of times is it correct? Yes. Now what I'm asking is, can you put these values and let me know what if, and our job is to find y at x equal to 3, right? Can you put x equal to 3 and let me know what should be y of 3 from here? Let me know. Yes, as you computed already, you substituted 3, you came to know that y of 3 equals to 10. Okay. Can you see from the data y of 3 equals to 10 makes sense, isn't it? Does it make sense? Why? Because at y equals to 2, at x equals to 2, y was 15, and at x equals to 4, y suddenly became 5. So it started to decrease. The function value started to decrease from 15 to 5. So value should be around 15 to 5. It is expected. And which is exactly you see 10, which follows the decreasing trend. First 15, then 10, then 5. So hope you got a hang of this method. Yeah. How we can compute the interpolating, like this is known as the finite difference table. This is known as finite difference table. This is known as a finite difference table, which helped you to find the finite differences. And through these finite differences, it helped you. Finite differences are nothing but the coefficient polynomial, isn't it? Finite differences, first order finite difference, second finite difference, third finite difference. These are all the coefficient of the polynomial. You can easily see these coefficients here. And those coefficients you found out using the table. After that, you got the polynomial. Then at which value you want to evaluate the polynomial, substitute that value. Okay, then you will get the value at any interpolating point. I hope you got the hang of this idea, right? Note down this. This is for the assignment. This is the compute y at x equals to 0.25 for the given data. Okay, you have x, you have y, 0.1. This is 9.9833. For 0.2, the value is 4.9667. For 0.3, it is being given 36. For 0.4, it is being given 2.4339. For 0.5, it is given 1.9177. You have to compute y at 0.25 in between these 2 points, okay, for this given data. Show the finite difference table, interpolating polynomial, okay, and let me know, okay. This is the assignment for you. Hmm? So now, like, wait, everyone attention. We are in a flow. We are in flow right now. Don't break that flow. Okay. So what you observed from this, previous method, every method is connected to the previous. Okay. Now you came to know that the Newton's interpolating polynomial is equal to how you can compute these are the coefficients. It is a polynomial. It is a polynomial, but what are the coefficients of that polynomial? What are the coefficients of that polynomial? They are finite difference. They are the finite difference, right? These are the first finite difference. This is the second finite difference. Third finite. These are the coefficients of your polynomial, right? This is exactly B naught, B1, B2, all this, isn't it? Yes. Now, even a more efficient method than the Newton finite difference is something known as the Lagrange interpolation. Okay, this is another method where you just change the coefficients, Okay, so I will let you know this is just another method since it is the flow of the previous method. So I'm trying to cover it here. Okay, so please give utmost attention to this because Lagrange interpolation is one of the finest interpolation techniques. Lagrange and finite difference interpolation are the two finest interpolation techniques. Okay? So please give attention and everything will flow accordingly. Okay. Then we'll see a few Python codes if time permits. Hmm? So this is something known as the Lagrange interpolation technique. Okay. So then what researchers ask is, we are facing a lot of issues with the coefficients. Okay. So can we make the coefficients more easier actually, such that we don't have to do with a lot of differences, lot of division. If you see, the finite difference was having lot of differences and divisions. That was a bit confusion, right? So it was not that intuitive. Okay. So Lagrange is a bit more intuitive method. So for that, we use something known as a Lagrange polynomial. Previously, you had Newton's interpolating polynomial. Similarly, here you will have something known as a Lagrange polynomial. Again, it will be a polynomial which passes through all of your given data points. The same idea. Again, the data points will be given. We are trying to, all this method, we are trying to find the better polynomial which fits the data. That's the idea. First, we used linear interpolation. We found that no, that we know the limitation. Then we came to Vandermonde matrix. Okay, polynomial interpolation. There we saw there are two limitations. Therefore, we saw that yes, we need more refinement. Therefore, we came across Newton's finite difference. Now we saw in Newton finite difference that it is efficient. We computed values of using interpolation, but they had a lot of divisions. Okay, now to avoid that, to make it even simpler, is the Lagrange interpolation. Instead of Newton's interpolating polynomial, we will use Lagrange interpolating polynomial. What is the method? We'll see. Okay, this is the last method for this. So what is Lagrange polynomial? Anyone learned about this previously? How many of you? Okay. So let us see. It is just the same. It is just the same. You will denote it by y as your Newton's finite difference formula. Fine. Y equals to something known as L naught x. Now, instead of Newton's finite difference, you have something known as Li's. These are the coefficients. L stands for, yes, good guess. L stands for Lagrange, and these are the interpolating polynomials. L naught x. These are the coefficients. Okay. L naught x times f of x naught, intuitive, plus L1x times f of x1, so on. You continue till your last data point. What is your last data point? Lnx f at xn. Okay. So this is what Lagrange interpolation looks like. Very, very nice form. Nothing complicated. Okay. It is a bit easier than the previous one, isn't it, as compared to the finite difference? So, but what you already know? What you already know? Maybe I did a mistake here. I'm using the notation y, but I thought about function. So let us use y throughout. Yeah. Do you know y at x1, y at xn? Yes, of course, because that is what is given to you, right? All these are known to you. What is unknown? L0 x, L1 x, so on till ln x are unknown to you. These we have to find. So that means you have to find the expressions for these LIs, isn't it? That's your goal. That's your goal. Okay. Indirectly, you summation of Li of x times f of times y of exactly, yes. And I is going from yes, exactly. So this is what Lagrange polynomial looks like. Okay. So yeah, I will not go into much details. These are known as the basis functions. These L0, L1, L2, and Ln are known as the basis function because you are writing as a linear combination of that. But don't worry about it if you have not heard about it. If you have not heard about basis, there is no worry. Okay, just know that we write it in this way. Okay, you just need to know the method. Okay, therefore, the course name is numerical, like part of numerical methods. Okay, this is the basic numerical methods you are learning. If it is numerical analysis, then we have to learn why this method works, all the proofs and bit of theorems and all. But that's not the part here. You just need to know the method here. Okay. So this is what Lagrange interpolation, interpolating polynomial looks like. Fine. So how we can find these LIs? That is a question. Okay. So what we can do is substitute these x points which you already have, isn't it? So what points you have? X0, x1, so on till xn, isn't it? Take any xk from this. Take any xk from this. What is the value at that xk? What is y at xk? Can anyone tell? At x equals to xk, suppose. Then what is y at x equals to xk? Any ideas? So you will have L0 at xk, right? But y at x0, isn't it? What you just did, you instead of this x here, instead of this x, you just substituted xk, nothing else. Yes, then what is happening? L1 times L1 of xk times, yes, good. So until ln of, exactly. Okay. So can we write this in some notation? That's what I'm thinking. Can you write this as some notation? Here some of you might have confused, like some of you might have thought whether it is correct, because there is L0, then there is xk inside, and there is y of x0 again. So there are a lot of notations circling around. So can we make it a bit more easier notation? That's my understanding. Can you think of it? I will soon write it. So can we introduce a notation CIK? CIK is a constant. Okay, CIK, that is just Li, that is ith Lagrange polynomial at evaluated at xk. How many of you are getting it or did not understand? Is it okay? Why I took this? Because L0 and you are evaluating at xk. L1 you are evaluating at xk. Ln you are evaluating at xk. So I need Cik to denote Li evaluated at xk. So can you tell me what should be the first guy from the top? C0 K y at x0, yes, plus C1 K at multiplied by y at x1, so on till Cn K y at x1. Can we write it as a summation? Summation C I K evaluated at y at x I, isn't it? Is it okay? And I is going from 0 to I is going from 0 to n. Yes. For you, like just to okay. So you know how the pattern is moving across the series, across this summation series. What we can do now? What we should do now? What should be our next step? Think. What should be our next step? Mhm. Can you see it coming? Can you see something is coming ahead? Can you see that now if I tell you, suddenly you will start finding the value of LIs. Suddenly everything will unfold quickly. After just if I tell this step. So can you see what is going to happen? Shall I tell or you want to think? Yeah, I'll tell. Okay. It is easier. I thought you could have told this. So let us see. Um, what is y at x equal to x0? Why not? Right? Why not? In notation, why not? That is equal to, based on this formula, L naught x naught. Yes, L naught x naught, right? L naught x naught times y at x naught. That is y naught, right? Maybe I'll write this as y naught, just because. Yeah, y naught plus L1 of x naught, y1, so on, Ln of x naught, Ln of x naught times yn, isn't it? Is it okay? Can you see what is going on? Can you tell me the values based on this? Just simple equation. What is the left hand side? What is the left hand side? I'm not hearing you. What is the left hand side? Louder, loud. Everyone should say what is the left hand side. What is the right hand side? No one wants to say. Yeah, but yeah, so now can you see something happening? Is there a y naught term on the left? Is there a y naught term on the right? If y naught equals to something involving y naught, what should be it? It should be 1. Then remaining 0, right? In order to satisfy this, this implies L naught has to be 1. L naught at x naught has to be 1, isn't it? L naught x naught has to be 1 because this is 1 times y naught, this is something times y naught, and there is no y naught after this. So it has to be 1, and L1 x naught equal to 0, L2 x naught equal to 0, so on, Ln of x naught equal to 0. Isn't it? So I told you, just by one step, you will uncover everything. Okay. Now, can you tell me what is y at x equals to x1? That is y1, right? What it should be? L0 times x1, y of x, y0, yes, plus L1 at x1, y1 plus L2 at x1, y2, so on till Ln of x1 times yn. Is it? Yes. Now, can you tell me what is going to happen? So what you got from here? L naught of x1 equal to 0, right? Because y naught is there. it has to be equated with y1, and this is L1 x1 times y1. So what you should have, L1 x1 equals to 1, but others should be 0, right? L2 x1 equal to 0. Others whole ln x1 equal to 0. Now from all of these values, are you observing something? No, I never told about identity matrix, but I am asking you, can you make a pattern based on this Li at xi? What is Li evaluated at xi? Others like Li xj where I not equal to j? Get out from you, like get it out from you. Okay. So just observe that Li xj is equals to 1 if xi equals to xj, and it is 0 if xi is not equal to xj. That's it. Isn't it? Why that is the case? You can see L0 x0 is 1. L1 x1 is 1. Others are totally 0. Others are always 0. Can you see this pattern? Can you see this pattern? What do you think? How this should look like? Can you predict? Can you predict the form of Li? Li is a polynomial, right? Do you remember that Li was a polynomial? Li of x. Li is a polynomial. So we have to find the expression of that polynomial, isn't it? So I'm asking like, now you have this formula with you that Li of x is a polynomial, fine. This is a polynomial, but we have something more. We have some more information. We have the information that Li of xj is equals to 1 if xi equals to xj, and it is 0 if, sorry, not xi equals to xj, my bad. If I equals to j, right? If I equals to j, here also I did a mistake. No one said to me anything. It is just based on the indices you are doing it, right? Not based on the x values. If I equals to j, it is 1. If I not equals to j, it is 0. So same for I not equal to j. So based on this, can you find the Lagrange polynomial? That's the idea. Any thoughts? Any thoughts? Mhm. So suppose like now you know that since Li at some points, some nodal points that you have given in your data set is equal to 1, that means you can think of, this is a guess. This is an intelligent guess. This is an intelligent guess. Okay, this is an intelligent guess. That how about we write the Li of x as a product of x minus xi's, like x minus x naught, x minus x1 into x minus x3, so on. That is the intelligent guess. Okay, this is not intuitive. This might not be the case that why it has been taken, but since like Li at xj is equal to 0, that means there should be a term x minus xj, right? So that when you substitute xj, it is difference is 0, and since it is being multiplied with some other quantity, it is 0. Are you getting the just the intuition a bit? No? No. Okay. Let me write it this way. Suppose. Believe me, for this case, just this expression. just this expression. I will tell you why this is true. Uh, yeah, yes. Do you feel that this can be a product? This can be a formula for Lagrange polynomials. Why I'm telling you is, if this is the form of that and you are substituting x equals to xj here, Li of xj, okay, and suppose you want to compute Li of xi, what we found, Li of xj is 0 if I not equal to j, isn't it? If it is 0, that means in this expression there should be something like x minus xj, right? Because if you substitute xj, then this xj minus xj will be 0. Okay, and it cannot be alone. It cannot be alone. If it is alone, it would be a linear polynomial. Okay, it would be a linear polynomial. But our Lagrange polynomial is not linear. If linear interpolation, right? So it is something different. So it cannot be linear. So it has to be multiplied with some other quantity, so that when this guy gets 0, it doesn't matter what is there here, the result is still 0. Are you getting? No. How many of you are getting it, or how many of you are not getting it? I want to see. Like, then only I can proceed. Mhm. How many of you are not getting it? Okay. See. Mm, yeah, maybe it is suitable for next class. Okay. So, yeah, you have two assignments next class. One assignment you have to submit me. Another assignment I will randomly call here anyone. Okay. I will randomly call anyone to say to me that whether what I did for the finite difference is correct or not. A lot of you got different results.